This is the second video in a series where we're learning to calculate the concentrations at equilibrium. For this particular example, we're choosing the same chemical equilibrium as in the first video. This is the reaction of hydrogen with fluorine to generate hydrofluoric acid, which has an equilibrium constant with this value. Okay, that is the long form notation, short form notation, and the value of the equilibrium constant is 115. Alright, so in this video we're going to learn to calculate the concentrations at equilibrium for a particular example which is a little bit more complex than what we have seen in the first video. So our initial concentrations are going to be 1 bar of H2, 2 bar of fluorine, and then there's no HF initially in the reaction mixture. And we have two questions. The first one is to predict what is the direction of the reaction, whether it's going to be displaced towards reagents or towards products from these initial concentrations as it reaches equilibrium. And then the second is to predict what the concentrations of each one of the species, or in this case the partial pressures, would be once equilibrium is reached. Okay, so the first question is whether the reaction will be displaced from reagents to products or products to reagents. That is a fairly easy question to answer here because you don't have any products. And what that means is that, well, if any reaction takes place, then it's going to be in the direction of generating products. Okay, so another way that you can get to the same conclusion is by calculating the reaction quotient, which in this case will be the partial pressure of products, which is 0 bar, over the partial pressure of reagents and the two reagents, which will be this. Notice that this is a value of 0. This is smaller than the equilibrium constant, which has a value of 115. So again, this means that the equilibrium is going to move to the right towards product so that the reaction quotient can grow and eventually reach the equilibrium constant. Okay, so we know that there's going to be some product generated when we mix reagents and products in these concentrations or partial pressures. The second question is, well, what will be the exact partial pressures once equilibrium is reached, departing from these initial partial pressures? And for that, what we're going to do is invoke here the ice diagram that we learned how to do in the prior video. Okay, so we have 3 rows, one for the initial partial pressures, another one for the change to those partial pressures as you look for equilibrium, and then finally what will be those final pressures once you reach equilibrium. And we have to do this for each one of the species, H2, fluorine, and then hydrofluoric acid. And all of these pressures will be in bar. Okay, so initially we have that there's 1 bar of pressure for H2, 2 bar of pressure for fluorine 2, and then no pressure for HF. Because we know that the reaction is going to move from reagents to products, then the change to H2 is going to be some reaction minus X. We don't know exactly what that is, but that is exactly what we're trying to determine in this problem. Because the stoichiometric coefficients are 1 and 1 for hydrogen and fluorine, then the same amount of hydrogen that reacts will react to fluorine, so that will also be minus X. And then HF, the stoichiometric coefficients are 1 to 2, so the growth in HF will be 2x. Whatever this x is, you'll have twice of the HF produced in that particular reaction. Right, so we're now ready to estimate what will be the concentrations or the partial pressures of the equilibrium. This is just the sum of the initial and the change rows. So that will be 1 bar minus x, 2 bar minus x, and here you will have 2x. Okay, great. So in the rest of the problem, what we'll try to do is see how we can solve for this unknown x by using the equilibrium constant. Okay, notice that the equilibrium constant is a value of 115. That has to be equal to the partial pressure of HF at equilibrium, which is this value, squared. Okay, so we have here 2x squared. And then the partial pressures of reagents at equilibrium in the denominator. Okay, so that will be 1.00 minus x, and then 2.00 minus x, and then this is equal to the value of the equilibrium constant, which we know. Alright, this is where this problem turns to be a little bit more complex than in the first video, because in this case we don't have a perfect square. Okay, you can simply take the square root of everything because you don't have a perfect square here in the denominator. right? So instead what we actually have to do is operate and then see what the resulting equation is. In this case, notice that you're going to have terms that depend on x squared and then terms that are going to depend on linearly on x, so that is going to be a quadratic expression. Okay, when you operate carefully through this, you find that that equation turns into 111x squared minus 345x plus 230 is equal to 0. Okay, so obviously this is a quadratic expression that you would need to solve, and again this makes this problem slightly more complicated than the first one. Alright, so remembering what the quadratic expression is, x is equal to minus b plus minus the square root of b squared minus 4ac divided over 2a. And remember that that a is the coefficient of the quadratic term, the b is the coefficient of the linear term, and the c is the other coefficient. Okay, so that is essentially what you have right here. Right, so when you apply the quadratic expression with these numbers, you're going to get two roots. Okay, so those x, you're going to have two values right here, and it will always be the case that only one has a good physical meaning in our particular problem, and we're going to see exactly how this works. So the first value of x that you obtain out of solving this quadratic equation is 2.15, and then the second has a value of 0.968. And again, only one of these will make physical sense. Let's take the first one. X is equal to 215. X is the partial pressure that has reacted. Okay, we go to the partial pressure of H2. Notice that 2.15 bar of H2 is impossible for that to have reacted, because that would mean that at equilibrium you have a negative pressure for H2, and that simply can't be. So clearly 2.15 is in this case the partial pressure that is not physically reasonable, because again this will mean that you will have negative partial pressures of H2 and F2 at equilibrium, and that doesn't exist. Then what has to happen then is that the second root is the only one that is physically reasonable, and that's the one that we're going to be using. Okay, so if x is equal to 0.968, then we can come here to the equilibrium concentrations and replace x by the root that you obtain right there, and then this is going to give you an equilibrium concentration of 0.03 bar for H2, then we're going to have 1.03 bar for F2, and then for HF that is going to be 2x, so that will be 1.94 bar. Okay, so that ends our problem. This will be the partial pressures at equilibrium if you start the reaction with 1 bar of hydrogen, 2 bar of fluorine and HF. We can do a final check, and that is to make sure that if we now plug these numbers into the equilibrium expression, we should recapitulate the value of the equilibrium constant, which is 115. And here you only have one significant figure in your calculation, but when you type those numbers in the calculator, you will find that you do recapitulate that equilibrium constant, so the problem is well done. Okay, so in this video we have seen a second example of how to calculate concentrations at equilibrium. The particularity of the video was to employ the quadratic formula to solve the quadratic formula that the quadratic equation that emerges when you try to solve those concentrations at equilibrium.